Hello students, welcome to our next lecture on BA networks. In previous lecture, we explored that what preferential attachment would mean in the context of BA networks, and we also showed, at least with some approximation, that why degree distribution for such networks would exhibit power law. Now, we are going to ask another important question from BA networks, that what if we either remove preferential attachment or growth? Can we still expect BA networks to mimic power laws that we see in the real world? Now, if you remember, we took an assumption of this continuum and we said that we can write this ki, where I is the node arriving at time instant t, as ki t plus delta t equal to degree of the node at time t plus some function what we call as an attractor function ki delta t multiplied by m in case these m nodes are coming, or you can also replace it by the constant a, for which we can replace based on the model that we are going to use. Now, in case of preferential attachment, we said that our phi k I was equal proportional to ki upon summation over all j's except the new incoming node as ki. However, when we say that there is no preferential attachment, we can say that this phi ki can reduce to 1 upon m naught plus t minus 1. That is, probability of one stub attaching to any node is simply equal to 1 divided by number of nodes that are present at time instant t. That would mean we can reduce this equation 1 to the form that del kit upon del t equal to a, again in this case would be m, because if m, this new node is coming with 3 stubs or 4 stubs, n can take that particular value as per our last discussion. Hence we can write, for using the form that I just put in the black box, into 1, del kit upon del t can be written as m upon m naught plus t minus 1. And when we integrate it, we can say that ki should be equal to m, and the degree of node that arrived at ith time at time instant t should be roughly function of m log of t, and we will put the limits ti and t. Now basically again I am saying is that the t is much larger than m naught minus 1, because when we start with the network we start with 1 or 2 nodes, and hence for sake of simplification, again because we are deriving a relationship that give us an indication and we are not caring too much about the coefficients or the parameters other than the gamma as far as this derivation is concerned, and hence we can reduce it to ki t minus m after putting limits m times ln t upon ti, which implies kit is equal to m into 1 plus ln t upon ti. Again, if we have to derive a condition, that what is the condition that kit is less than k, we can write this as m into 1 plus ln t upon ti less than k, or we can say that ln t upon ti is less than k upon m minus 1, which implies t upon ti is less than e to the power k minus m upon m, because I take anti-log on both sides, and hence ti has to be greater than t into e raised to power m minus k upon m. And what this would mean, that let us say that there are certain node that arrived at time ti and currently we are at time t, and we want to see that how many nodes arrived after the time instance ti. So since we are measuring everything from origin, we can say that this interval is equal to t minus ti, and if there are m naught nodes already present at 0, so we can say that this is m naught plus t minus ti. And now if somebody asks us, can you tell us on an average what is the probability that kit is less than k, And now we have already derived the relationship that all the nodes without preferential attachment, if they are arriving after this time instance, they are going to have on the average degree or the degree of that particular node less than k, and such nodes would be m naught plus t minus I, because based on the similar discussion that we just had here, or minus ti divided by m naught plus t. And now if we replace this expression, this would be 1 minus e raised to power m minus k by m, which implies probability of k is function of exponent of e raised to power minus k upon m. And hence that means that if we deviate from preferential attachment, there is no preferential attachment. In this case, there is no power law. Similarly, if we consider other side of the hypothesis, that let us say that there is a preferential attachment but there is no node growth. That means the new node that was coming at each time step is now not entering into the system, but we have some preferential attachment, that is at each time step t we will add a new edge into this particular network until we reach a complete graph, because after complete graph there is no point of adding the duplicate path or repeating edges. Now in their work, Rekha Albert and Albert Laszlo Barabashi again applied the mean field assumption to same kind of analysis and said that we can still write in continuum kit plus delta t would be equal to kit plus the term on preferential attachment for node ki multiplied by delta t. Now in this case, we say that there is a still preferential attachment for node ki is there. So let us take this I inside and we write this as ki. We say that this is proportional to ki divided by sum of all other nodes present at particular time instant t, and there is no incoming node, and hence you can count the total number of edges and leaving the one edge that would be entering system at a new time. Now we can replace this proportionality constant by equal to sign and say that this is equal to a. As in previous case, we said that each new incoming node was having m number of chances or m chances to connect to a new hub. In this case, if a new edge is entering into the system, the chances it would have is n divided by n minus 1, because it can connect to n nodes divided by n minus 1 is accounting for the fact that no self looping is allowed, that is it cannot connect to itself, and we are eliminating this case. And when they substitute this, and I will post the link to detailed derivation in the description, they say that this pi ki can be written as a times ki divided by 2t if one edge is coming at a given time, plus when you are selecting a node from where this edge will originate, the chance of doing that is again 1 by n. So if we say that we can choose any node out of this, and from this node which can be selected with probability of 1 by n, we can terminate this particular edge on any other node where that connection is not exhibited, and hence this takes a form of del ki upon del t equal to a ki upon 2t plus 1 upon n, where a is shown to be n upon n minus 1. Now again we will not worry too much about the mathematics, and in detailed derivation when we take the integral, we say that ki by t is proportional to 2n by t plus c to t to the power 1 by 2, and for boundary conditions c is calculated to be 0. That would mean that kit can be approximated as 2n multiplied by t, and this says that after certain transient time, let us say that t is much greater than n, you would see that this ki upon kit becomes constant or time invariant, because after that each node will get their own linkages and hence this growth of the network will stop. And initially network will have a different distribution. As the network grows, we tend towards a stabilized system where no growth is happening, and hence we say that the degree distribution, when we have no growth but preferential attachment, becomes a non-stationary distribution. This is again, it is in contrast to the finding of various networks that can be explained by BA network theory, which are said to exhibit power law throughout their degree of evolution. For example, if you leave out, let us say, when there are 5 or 6 nodes, that would be meaningless network to analyze. But after network gains some critical mass or have some finite number of nodes, it is shown that BA networks throughout exhibit a stationary distribution which can be explained by power law, and again, hence again the hypothesis that we can explain real world networks by either using preferential growth or using and no growth, and alternatively only growth with no preferential attachment does not stand ground. And hence we say that for network to exhibit power law and hence resemble to real world system, it should have a preferential attachment as well as show growth with the preferential attachment. And these were the two key findings of BA networks that help us explain many real world system. Now when we talk about the average path length, since we derived that gamma is equal to 3 in case of BA networks, average L from our discussion on regimes can be calculated as log n upon log n. And similarly, clustering coefficient or C for BA networks is proportional to log n square, or I should put this outside, divided by n. Now if you remember, in random networks we saw that if we, for a given k, this clustering coefficient was proportional to 1 by n, which is very different from the clustering coefficient observed in the case of the BA networks. So that would mean that if you look at compare 1 and 2, BA networks are generally more clustered as compared to random networks, and that is one typical signature that we see in the case of BA networks. Now with this we cover a lot of aspects of BA networks, that what is a preferential attachment, what if we remove either preferential attachment or we remove network growth, and how the scale free property cease to exist. And in applied world, this would be good amount of information as you go towards your class projects.